Okay, Bismillah ar-Rahman ar-Rahim. So today we are going to talk about the new chapter 16, which is going to be the last chapter we are going to cover this term. And this chapter is about clutches, brakes, coupling, and flywheels. Now, among the most important part here, the brake and the clutch, um, we're gonna see why we were talking about bearings, gears, why clutches and gear and brakes deserve to be in this book for one whole chapter. If you go and dismantle a machine, there are too many other things. So why these? This is a good question. And before I move on, I would like to highlight the outline for you. This is the outline. I'm not gonna go over it one by one, save the time, but the chapter, which is the section 16.6, is highlighted in orange. This is disc brakes. So this is the ABS, ya shabab, that probably today we all have it. Of course, most cars have an ABS braking mechanism in the front wheel, and then in the rear wheel they have a drum mechanism. And this is reading assignment. ABS, alternating braking system, which basically apply the brakes in an alternating way. Um, and of course, we have section 12 and 11 excluded. We're not going to cover them. They are not included. The disc brakes are reading material. Okay, reading material means you have to read it and make note of it, Ishabab. I cannot guarantee. Maybe you will have in the final multiple choice questions which involve the some reading material from this section. Okay, now this is an these are some examples about um, breaks. As we said, we have the disk, as you see it over there. This is the sorry uh, this is the ABS, and this is the drum. The drum, it's a drum, multiple shoes, and these shoes expand, and when they expand, there is a pad, which is the braking material, the frictional material, and basically brakes help dissipate kinetic energy. These are too common. The third one here is a conical shape, and here we have a clutch. Clutch, ya shabab, is used in manual gear system, and uh, you know, I honestly probably the truth is I don't know if the clutching mechanism exists even in automatic. I think it makes sense. It does. Okay, in automatic gear. But in the end of the day, what happens here is that you have a moving part with a frictional material and another part, and then when you push the the part which is moving, let's say it is reciprocating like this, and then you push it against another one, and because of the frictional material, they kind of, and the force that you are pushing with, they get stuck and they move together. This is basically clutching. This is an external braking system. So you can imagine over here, I'm talking about this guy, you can imagine that you have some sort of a disc, a journal, whatever, being in motion. And you see these pads, ya shabab, these are the frictional material, which going to squeeze around it. And then, of course, in all of these, actuation is very important. So in here, you have a mechanism which actuate, push and pull. And this is how the brake is being applied. Same thing here. You have an actuator on the disc to alternate this pad being in touch with the disc and not. Same things here. The mechanism in a drum will actuate the shoe to expand, and then, as I said, being under friction with with the with the surface and dissipate the energy. Now, in all of these, okay, ya shabab, most important part here is that when you apply this actuator, this actuating force, and then the frictional material come in touch, you have a pressure. You know, first of all, this pressure should be exactly measured such that this pad doesn't crush, right? The pad, ya shabab, is made up of a most of the time some sort of a material which is polymeric in nature. It it does not. It's not metal, so it will crush if you apply significant force on it. So we need to know the pressure distribution, of course, which relate to the forces and the friction and so on. We need to find relation between the pressure, the maximum pressure, and other pressure, because you will always have some sort of a distribution. There is no single point here. And then you want to know that using equilibrium, what are the forces? Huh? You know, these pads and everything is connected by pins and bolts and screws, so you want everything to be safe. And to do that, you may need to make sure that the forces will not shear off uh, these bolts or screws. So we'll find the torque, the reactions, and so on. So what are we going to do, ya shabab? We are going to start by a simple example here, which is a little bit funny but effective to understand what's going on, which is a door stop. If you look at the door stop, you know it, ya shabab. You put a mechanism to keep the door open or closed, right? So you put some sort of a hydraulic pump at the door, and then when you open the door slams slowly. And to prevent the door from closing, and you can use a shoe. This, I mean, a door stop. A door stop is hinged by bolts in this way here at this point in red. And because you allow rotation, you can take this door stop up or you can put it down. There is no moment. Rotation is allowed. So the only thing that you have here is is reactions. And and then when the door pushes against the doorstop and the doorstop basically is in touch with the surface, there is this black material, ya shabab, is what is basically the frictional material. Okay, so that frictional material will be pushed by, the door is pushing here, and then the mechanism is inclined, so you will end up with a resultant force going downward, pushing against the surface. The surface will react by a pressure. Now here we're assuming that this door step is in a three-dimensional uh, as a three-dimensional geometry. It's a rectangle, so the depth is going inside. What you see over here, what you see over here is this distance is W1. But in the page, there is a depth which is the W2. So W1 by W2 is equals to this rectangular area. Now you will see, ya shabab, that if the shoe, and you will see that this is something that we are going to talk about a lot, which if the shoe size is small, then that distribution is not far from uniform. You understand? So if the shoe is small, you may end up with a distribution which is like this, which by the way is not very much different than a uniform, rectangular distribution. But if the shoe is big, okay, you may end up with a distribution like this. And in that way, the assumption that this is uniform will make a lot of, significant error. But that's why we're saying, is it a small or is it not? You understand? Now, few basic issues here you need to care for. The reaction Rx, Ry, the line where the reactions is happening, okay, all the way to where, so the line here resemble the distance from here, this to this is B, that's we call it B. The distance from the reaction line all the way to the surface is A. So A and B, two reactions. The force, which is now actually the actuating force, is F, and it is applying downward. And then the pressure is down. Now the pressure is being described as a pressure function of U. What is U? Look, there is a distance C, which is right from the beginning of the line of the reaction at the pin all the way to the beginning of the shoe, and it is called C. After C, from here all the way to here, we have a function U. That U changes from the beginning all the way to the end, and as we move on, we see that the pressure is changing. The average, you know, is here U bar. Okay. So what is important is that with this configuration, we can have a leftward movement, which would result in there are two reactions acting one to the right, positive X, positive Y. This is the actuating force downward. The normal force will act upward, and the friction force will act on the left. If you have a rightward movement, you will end up with the Y reaction going downward, the X reaction going to the left, the actuating force is still down, and you will have the normal force acting upward and the friction force acting to the right. Now, you see, this problem is solved for the same actuating force. Yet, just because of the movement, rightward or leftward, you ended up with different reactions, different frictional forces, and different normal forces. You see that? This one is the same, but with a rightward motion and assuming a trapezoidal distribution of the pressure. Now, this is just an example to show you what is involved here. An actuating force, a pin reaction, a friction force, and a normal force, and so on. And there is even torque. So, but we are going to use this door stop to explain a more fundamental terms in terms of a braking. You know, whenever you apply a brake, what are they? Well, if, for example, we assume that this is the same thing, a door stop, and we have the point A right there, which I marked capital A, I marked in red as the hinge, and the shoe over there has a frictional material, and this is the surface. And again, the distance from the reaction to the surface is A, the distance from the Y reaction to the actuating force is B. And let's assume that the motion is going in this direction. The friction force is going against the motion, which is F by N, and this is the normal force. That's it. That's what we're doing. Now, we will make an assumption that first, that the shoe is small, and for that, or short, and for that the pressure is uniform. Okay, and then we will assume that the pressure which is generated is equal to PA. What is PA? PA is the maximum pressure. What is the maximum pressure? As I said, you can expect here that everything is made from the door step is made from steel. The surface might be marble or something very hard, and then the little shoe is made from non-metallic material which can get crushed. So it has a maximum pressure that can be sustained within that material. So let's assume that our limit here is to apply what is going to generate a maximum pressure, PA. We call it PA. PA stand, I think, for an allowable pressure. Okay. Now, what is the normal force? The normal force will be equal to the pressure PA multiplied by the area, right? So the normal force here is what? Force is equal to pressure by area. If the pressure is PA, and you know that this shoe has an area, a length by a depth, whatever it is, which is basically W1 multiplied by W2. But I'm calling it an area just for simplicity. So this is PAA. All right. Now, if I sum up the moment about A, let me clean up this. This is going to be important to have it clean. Okay. If I take the moment about A, let's start with the actuating force. The actuating force is multiplied by the distance B, and then it is causing a rotation which is counterclockwise. So I'm going to call it positive. So if B is positive because it's counterclockwise, then we have also the friction force, which is this force multiplied by what? By A. And then it will cause also a counterclockwise. So this is why it is positive, and it is Fn multiplied by A because it's counterclockwise. What remains is the normal force. The normal force is the same as the actuating force, but it is acting upward, multiplied by B, but it is rotating clockwise. And that's why we have it minus NP as a clockwise moment. Remember, N is equal to PA, correct? So if you substitute N as PA in here, and then solve for F, you will end up with this force. Now, this is the actuating force, okay? That will generate the maximum pressure on that little tiny black frictional material, okay? All right. Now, I think the rest is very simple. If you sum up the forces along the X, you will know what is, this force is against this, and then this force and this against this, and then you will know what are the reactions. Good. Now, this is not the detail. This is pretty straightforward. Let's move on with the nomenclature of braking. Now, if you go back to the equation, okay, when we set the motion to the left and the friction went to the right, we ended up with this equation with a minus sign here. What does that mean? It means, remember, Shabab, if there is no actuating force, there is no friction, there is no brake. Here, it's very interesting. When you apply the actuating force and then the shoe pad touch the surface, friction is going to reduce. Look, look, B minus FA. So it's like a friction term is reducing this parenthesis, which will reduce F. So it's like by applying the friction, things become easy. The actuating force that you will need to reach the pressure will become kind of less. And in that sense, you don't need to push further. You can reach to the maximum in an easy way. That's why the term self-energizing. It's like it energizes itself. The friction is just by putting the friction, you are helping yourself. That's it. Now, but if you flip the motion, the force dimension, direction will change, and you will end up with a positive sign. Here, a positive sign means there is nothing, and then you apply the actuating force, and then is there something wrong, ya shabab? Uh, do we? I think my iPad got disconnected. Okay, let me pause the recording and then get it connected again. Okay, it seems like the iPad is still suffering, so I am going to share my slide through the computer, which means I have limited capability to mark and point to things around, but I'll do my best whenever I can. Okay, so uh, so what I was saying, we will get a self de-energizing. And a D self in energizing means that when you apply the force, somehow you end up needing more. You just need to put more. That term is a plus, which means that you need to put more. The F has to be more in order to reach PA. You got that? So this is the very important. This idea of energizing, self-energizing, self-de-energizing is very important. Another thing, which is also important, is this. Now let's rewrite the equation again, which is F equals to PAAB plus or minus FA over FA divided by B. If you look at this parenthesis, Shabab, you can see my slide, right?
Yes, sir.
Okay,
Yes.
good. Yeah, okay, good. So if you look at this parenthesis, okay, then what happened is this. You want this to be greater than zero. Why? Because if this is zero, F will be zero. And if F is zero, it means that after you apply it, everything is cancelled out, then the brake is self-locking. And what does that mean? It means that it will lock. And it's not like you apply the brake and then you release it and then it unlock. No, it get locked. And you don't want it to be negative. You don't want it to be negative because it means you need a reversed load. You need a reversed load in order to undo the brake. So it's like you get in trouble. You are in the car, you push in the brake, and then you say, "Whoa, whoa, whoa! I need to go down now and pull the pad in order to unlock this brake." You don't want that, right? So this is why that term has to be uh, greater than zero. Now, for your knowledge, I want to tell you something. This may look scary, but it isn't. In the book, okay, in the book, ya shabab, what happened? The book derived what I showed you in simple terms in an integral form. Why? Assuming that the pressure, as you can see, has a distribution. But just to remind you, remember N, we said the normal force equals to P small a multiplied by the area. This is it. Look at it. It's a pressure average multiplied by W1 multiplied by W2. W1, W2 is the area, right? The reactions, if you go now one by one and compare them, you will see that this is exactly the same. Okay. Now, why did I make it that simple? Because I want you to see this energizing, de energizing, locking, unlocking in a very simple way. In the end of the day, a door stop is not the fancy thing that we want to do. We want to do way more interesting things, way more. So we did not to bring you here as engineers to do door stops, ya shabab. Huh? This is a joke. This is something that we give it to a student. When you become engineer, you will do way more fancy things than this. You got my point. Although, ya shabab, never underestimate anything. I mean, come on, you can make a factory and employ maybe hundreds of people to do these door stops. They are everywhere in the country and everywhere in the rest of the world. And if they don't function, you lose. And if they don't function, it means that your engineering has a problem. So I don't mean to undermine this. Actually, simple stuff has a lot of engineering behind them. And if they work, they work. They work because of mathematics, and you understand. Okay, what we want to talk about in more detail is this: the drum, an internal expanding rim, clutches and brakes. This is, ya shabab, the famous uh, brake, right? Drum. And as you see, these are the shoes over here on top, non-metallic material. And we have here a mechanism, which, by the way, if you go and open the drum in in your car, you can actually with your hand actuate these with your hand. Okay, so what are these things? You know, what are they? What do they usually consist of? The drum, okay, or a shoe rim, clutch, and brake consist of mating frictional materials, which is very important, means of transmitting torque to and from the surfaces, and actuating mechanism. You have to actuate. And the actuating mechanism can be an expanding rim, a centrifugal, magnetic, and hydraulic and pneumatic. Okay? In here, the P is not sound. You don't sound the P. It's a pneumatic, not bin pneumatic. So what happens is this. You get ready for an interesting surprise that this brake system in your car is not a joke. There is a lot behind it. And I'm not saying this to tell you that it is difficult. I'm trying to tell you that these simple things that probably some of you might be even involved in replacing them. I know people enjoy replacing their brakes by themselves, maybe in the past, not anymore. But even if you are an enthusiast who is doing these things, who really like to get his hand dirty and involved, I mean, you would think that, okay, this is simple, but there is a lot of delicate details on the shoes. So let's enjoy it. I don't want you to be scared. Actually, we're gonna give you the final equation, and we'll look really interesting. I'm trying to make you happy. This is what I'm trying to do. So first of all, in these things, what are we gonna do? You will see that we will pin the shoe at one location. By the way, you will see it this in the car. Go and just look at it. You will see that there is a hole in the shoe, and you will screw it. And then there is another one which is in front of a little cylinder. That little cylinder is basically an actuator, pushes the shoe. So this is the actuating force from the cylinder. And apparently, because you're actuating from one side and the shoe is curved, the assumption that the pressure is uniformly distributed is not valid. And in reality, we are going to come back and we'll see that, oh, it actually changes. And the pressure is going to be assumed to change in a sinusoidal way. But be careful, when I say sinusoidal, I don't mean it is like this. No. What I mean is that somehow, somewhere along a point, it will start from zero, the pressure, it will climb up, and then it will go down. There is no up, down, up, down, up, down. Just we know that the beginning of the sine wave is zero, it goes up and then dies away. So that's one. The next thing is to have the pressure, you know, um, uh, where is the maximum? If we have a short shoe, then the pressure is going to be, I'm connecting يا شباب, sorry. Okay, we're back again to here. So if you have the pressure, if this is a small shoe, then the pressure is gonna occur where? At theta 2. What is theta 2? Well, theta 1, okay, is gonna start from the beginning of the shoe, and then theta 2 is at the end of the shoe. Why? Because remember, ya shabab, if you look, you will see that there is a metallic mechanism which is pinned from here, actuated from here, but the shoe might be sitting like this. It's taking only part. If we have a long shoe, a shoe which is, you know, going like this, it's like one big sector, then the maximum is going to occur at an angle which is 90. We're going to see these coming soon. Okay, don't worry about it. Now, so how are we going to deal with this? Well, if you look, this is a very nice example, okay, in details. And I want you to look at the details. Why? Because we are not going to go in a very deep uh, and rigorous derivation to this problem, but basically what we have here, I'm gonna in red, I'm gonna show you that this is the shoe. Look at it only. However, the brake, but this is actually, I'm gonna call the red one the pad, but the shoe itself is this. Look at it. It's going all the way to here. You see that? It's taking almost a quarter of the circle. But the shoe is located only on a partial portion of it. Now, I told you that we are going to pin the shoe. That's why we have two reactions in there. And we are going to actuate it. So the yellow arrow is the actuating force, which is going to be inclined. And yes, you can know the angle and you can resolve this force into X and Y. There's no doubt about it. The reactions in here, we don't know them. We will just assume X and Y again. And of course, this is allowed to rotate. It is not fixed. There is no reaction moment. Good. Now, when you apply the actuating force, this pad in red will become in touch with the drum. Where is the drum? The drum is there. This is it. This is the drum which is surrounding the internal mechanism. And not only this drum is rotating in a clockwise fashion. This is important because the rotation will change the direction of the forces, and there are parts which will be subtracted, there are parts which must be added. And this is going to end up giving us this condition of self-energizing or self-de-energizing. You understand? And again, the competition between locking, not locking will come back again. So if you look here, what we have a point. I'm going to clean this up again. This is very important. I'm going to clean this up, and then I would show you here this point right there, a point of contact, and then we resolve the forces. When the pad is pushing against the drum, okay, there is a normal force acting. So in a differential element, little, remember, there is a surface, there is a pressure distribution. We're taking one single element. There will be a normal force. The normal force has to be perpendicular to the tangent, and there is a friction force which is acting along the tangent. Now what are we going to do? We will resolve the normal force into two normal forces, and we will resolve the frictional force into two friction forces, sine and cosine, sine and cosine. And we know that the reactions are here, and we know that this is the actuating force. Good. Now, let me show you. I need to clean this again. I'm sorry, Shabab. Going back and forth. Let me show you a little bit of more detail. We used to, we are gonna set up the coordinate system as x in the horizontal, y in the vertical, and we will, as usual, measure the angle from the positive x in counterclockwise fashion. So if you go from this line over here all the way to here, this line is the beginning of the shoe, the frictional material. Look at it, the gray one. And then if the gray end here, so this is theta 2. Good? Two angles. Another one, another important parameter is this guy, which is the C. C is the distance from the pin over here all the way to the actuating force. Okay? You know, you know these two. Let me show you before I stop, because I will stop soon in a minute or so. Uh, the detail. You will see that we can derive that the actuating force F is related to the moment due to the normal forces minus the moment due to the frictional forces, because these forces will cause moment. If I sum up the moment, I will have moment coming from the frictional forces, moment coming from the normal forces, divided by c. What is c? The distance, which is the moment arm for the actuating force. Yeah. Now, again, you can see that there is a normal kind of force being subtracted from frictional force. The same logic apply as the door stop. We need to make sure that the normal is greater than the friction in order to avoid self-locking. Yeah. And this is resulting from an actuating force for a clockwise rotation, which will generate self-energizing. If you flip the rotation to counterclockwise, you will end up with a self-de-energizing, and these two terms will be added. Yeah. In the next class, I'm going to show you how to calculate Mn, how to calculate Mf, how to calculate the torque, how to calculate the reaction forces, and everything. In another word, we will know everything about this brake. Okay?